Welcome to our second video about the quantum theory of NMR about Hilbert space. So in the previous video we discussed about how to describe our spin system, and we decided that the best way is to use the linear combination of stationary states. But this description it's not exactly handy, since it's okay for just 1/2 nucleus, but if we go to 2 1/2 nucleus, it became pretty crowded and completely messy for 3. But we have to remember one important part, that everything is described in terms of stationary states. So it means that the stationary states are actually the base for our spin system. And so here come Hilbert space. We can just define a base for our spin system, like alpha and beta, as I said, our stationary state. And so our psi just became a vertical vector, which the components are just the coefficient, C alpha and C beta. So we can just, at the beginning of all our calculation, decide which is the base, and we know that in every case the first position of the vector it's going to be about the coefficient for the first stationary state, in our case alpha. The same thing is hold true for 2 nuclei with just a longer vector. And if our spin system is described by vector, the operator that act on such vector are going to be metrics, here representing the Hamiltonian matrix. And if we apply to the Hamiltonian our generic psi, we obtain the exact same result presented in the previous video. There is a small problem, however, since in matrix calculation the product is not commutative. If I do psi times Hamiltonian, it's not an operation that it's possible. We need to use an horizontal vector. And to indicate that we want to use an horizontal vector, we use the bra. So here is the meaning of the Dirac notation in Hilbert space. The bra indicate an horizontal vector, while the ket indicate the exact same vector but in a vertical position. So bra horizontal, ket vertical. And so something interesting happened. For example, if we want to know the value of E alpha, I can just apply a pure alpha state on both bra and ket to an Hamiltonian. So I will sandwich my operator between this bra alpha and ket alpha. And the result is going to be the energy state of the alpha state, the energy of the alpha state. The same holds true for the beta state. And what if I just apply a generic psi? Well, the result is the energy of the alpha state times C alpha squared, that is the probability to find my system in alpha state, plus E beta times the probability to find my system in the beta state. So this operation gives me as a result an average energy weight on the probability to find my system in alpha or beta. And this is called expectation value. Now be careful, the expectation value don't actually say what is the most probable energy. I know that every single time I'm going to perform this measure, the result is going to be E alpha or E beta. And the Hamiltonian is going just to be, the expectation value of the Hamiltonian is just going to be something between these two values. It's just the average over an infinite number of measures. But the Hamiltonian, it's not the only operator. There are also another important set of operators, the angular momentum operator. They may seem not particularly interesting. Okay, are just this metric describe the angular momentum along x, y, z, but their expectation value is proportional to the magnetization along x, y, z. And now they became particularly interesting. But probably first you have noticed a pattern in all these discussion. We have in one side operators that just act on the quantum realm, and then we have their expectation value that just express quantity in the macroscopic world, something that we can actually measure. So the Hamiltonian tells us the energy, well, its expectation value tells us the energy, and the angular momentum talk to us about the magnetization. And this is a very important, it's a key point of the entire quantum theory of NMR. Since we are not actually able to see all these operators, we are only able to measure their expectation value. So we have a limited knowledge of what is happening in the quantum system. Now, to better understand this further abstraction that we are presenting here, let's say that we have magnetization of my system, and I want to describe it as it evolved due to any phenomenon. Also, just I'm applying a pulse sequence. And I would like to just go directly from one magnetization to another magnetization, as we have done in the vector model. But actually, in many cases, this is just not possible. We don't know directly how the magnetization is going to evolve in time or subsequent to a particular phenomenon that we are forcing on our system or not on the system. But what we can do is describe the evolution of the operator. So working on the quantum part of the system. And so I cannot directly go from start magnetization into end magnetization. I have to first convert my starting magnetization in the operator that describe it, then perform the evolution, perform all my operation in the quantum realm, and then when I reach the end, convert back my operator into visible magnetization. And that's another abstraction, and that's why the quantum theory of NMR is so important if you really want to understand what is happening. Because the vector model tried to force the evolution of just the expectation value, but actually what it's happened is the quantum system is evolving, and we are just seeing a small part of it through this very, very specific quantity that we can measure. Thank you for your attention.